You open your expense ledger app to find a transaction from a few months ago. You start swiping up rapidly, but instead of a smooth scroll, the screen stutters, chokes, and finally freezes completely. Below that frozen screen, a severe resource bottleneck is suffocating your device's memory. The application is trying to render a chronological list of data in reverse, and because of how the data is structured, that simple request is triggering a massive sudden demand on the system. That stuttering is the physical evidence of a brute force data architecture collapsing under its own weight. This singly linked list efficiently adds records by pointing forward, but it's a strictly one-way street with zero reverse pathways. To read backward, naive code copies every record into a massive secondary array. We call this O of n space complexity. Memory scales linearly with data. Throwing extra memory at a navigation problem scales poorly. For every 1,000 records you add, the system must card out another 1,000 blocks of space just to support the reversed view, eating into the resources needed for the rest of the application. To solve this elegantly, we need to achieve O1 space complexity, meaning the operation requires almost zero extra memory, regardless of the dataset size. To do that, we must not move the data itself. We have to change the rules of the road. Instead of copying nodes, we are going to reverse the connections between them. But doing this in place is dangerous. If you break an arrow without holding on to the next node in the sequence, the rest of your data floats away, permanently lost in the memory void. This is why we rely on a precise operation using exactly 3 tracking variables, or pointers: previous, current, and next. Together, these 3 pointers act as a protective scaffolding. They allow the system to safely sever and rewire connections without triggering data loss. Starting positions: previous at null, current at node 1, next at node 2. Step 1. Next secures the unreversed chain. Step 2. Current snaps its arrow backward to previous. Step 3. All pointers slide 1 step down. The loop repeats continuously to the end. Because we visited each node exactly once, our time complexity remains a highly efficient O of n. But crucially, our space complexity is now O of 1, because 0 new data was duplicated. This pointer manipulation allows the application to handle navigation without the memory spikes that cause scrolling to freeze. The logic does the heavy lifting, sparing the hardware from unnecessary load. This same logic scales up to much more complex problems. Consider an enterprise matching engine that needs to reconcile a ledger by interleaving the oldest and newest records alternately. We dispatch 2 pointers, one moving single steps, one double speed. When the fast pointer finishes, the slow pointer marks the exact center. We sever the connection down the middle, bisecting the list. The second half is then immediately reversed in place using the 3-pointer flip. This is the power of localized link adjustments. Developers can bisect and control massive datasets without ever actually touching the data payloads inside. The final phase is to weave our 2 prepared halves together. Using an alternating zipper method, we pull one node from the chronological first half, then the next node from the reversed second half, locking them together down the line. The ledger is perfectly reordered, reconciled, and fully merged, all achieved entirely within that strict O1 space constraint. Back on the user's device, that complex backward scrolling and sorting executes flawlessly, rendering the information in fractions of a millisecond. True software optimization is invisible. By understanding how to manipulate the structural scaffolding of data, the most powerful code proves to be the code that leaves the smallest footprint.